I am Soboh Qeeq. I am postdoc work with laboratoire de physique de plasma in Paris with Cenaris. And with this work has been monitored and supervising by Olivier Lecontel and Alessandro Rotini and George. It's my pleasure to present my automatic classification of a plasma region and detection of a plasma jet in near-Earth space using supervised machine learning. The motivation of this work, we try to have a big advantage of multi-scale magnetospheric missions, which provide a huge resolution of inside plasma measurement, and to try to improve the space plasma classification in different regions in the Earth's magnetosphere environment. We use FCN, which has been already done by EGU in 2021. And with this, it's so important to try to produce automatic method to classify and to provide dynamic plasma regions inside the Earth's magnetosphere to try to use different spacecraft data also. With this work, we try to apply these machine learning tools inside other missions has been observed inside the Earth magnetosphere environment, like a cluster and TEMIS. With this, with the EGU work, we try to label a different 10 different near-Earth regions in his model, for like solar wind, ion force shock, Bose shock, magnetosheet, and magnetopause, and plasma sheet boundary layer, and loops. And with this work, we try to add some other phenomena has been observed in the Earth's magnetosphere, something like magnetic reconnection, flux rope signatures, and depolarization fronts, or a plasma jet. And with this, we try to examine EGU work, if it's work for all MMS data or not. Like for one example, for what EGU did for day side and night side in the Earth's magnetosphere classification, we could see in the both figures we have in the first panel, we have the ion flux energy, and panel B, we have the magnetic field data for X, Y, Z in total. In third panel, present the density, the ion density, and fourth panel present the velocity for ions, and after that, present the temperature for ions, and the last panel present the product of the model label based on the signature inside measurements for MMS. And we see for both figures, like day side and night side classification, we could see the model has been create a high accuracy for different complex regions like Bose shock or boundary layer or magnetosheet, magnetopause, and all of these has been worked very well with EGU model. And now for our work, we try to examine this model for the whole MMS data from 2015 to 2025. And what we found the model is worked very well for the whole MMS data for 10 years, but there's some missing days, which is presented in this figure. You could see present all the successful work for the model inside all MMS data. And with this, we could see the model has been worked successfully with MMS data for 2015 to 2025. And now we try to make this model work with a cluster and TEMIS data, and which is still in a progress and inside an examination. And now for one phenomena observed in the Earth magnetosphere, which is called the plasma jet fronts, we try to put it inside the model. But before to do that, we try to see if there is some simple characterization or some simple criteria we could apply to get detection of the plasma jet directly or not. In this figure, we could present the magnetic field data in Y direction, after that in Z direction, and after that in the total. And in the fourth panel, we present the density for ions, and the last panel present the velocity in X. And we take some small criteria, like we have the significant change for the magnetic field data in By or Bz, more than 5 nanotesla, and for also we have the change of the angle, and we with this small criteria, with a simple code for Python, we could detect all of this. And now we try to apply the machine learning directly inside that to see if it could be detect all of these phenomena observed in the Earth magnetosphere environment, like plasma jet fronts and dipolarity front, like Soboh, or a magnetic reconnection directly, which will be the next step for this work. For the summary, we could, with the work with Ego, we found by using FCN network, we have successfully see 10K plasma region near Earth magnetosphere, near Earth by using 10 years of MMS data, which is worked very well. And now we apply it for a cluster and TIMIS to see if it will work again in the same accuracy or not. And with some simple parameters or a simple criteria, we could apply to identify and determine plasma jet or different phenomena such like dipolarization front or reflex or signature or magnetic reconnection, which could be worked very well. And after that, we will apply it for add it for Ego model, and to see if it's work very well for MMS data or other emissions. Thank you for your attention. Please, if you have any question.
Thank you very much. Are there any questions?
How was it validated for the high accuracy? And could you explain that chart that had the success measurements? What was that against?
Actually, with MMS data, we check it day by day, as you can see from this figure. And after that, we try to check it manually, me and Olivier and Alessandro, and we found that it's worked very well to determine all these different regions inside the Earth magnetosphere environment. That's why we think this model is worked very well.
So you manually verify the 10 years of data?
Yes. But it's okay. It's I create it automatically, and after that, every day we plot this kind of figure, and after that we check it one by one.
Are there any other questions?
Yeah, a quick one. So you mentioned at the end the summary that the classical method works well.
Yes.
So what is the classical method here?
We just mean about some specific criteria, like such kind of where when we apply for like dipolarization front, we say we have a sharp increase of the northward component of the magnetic field, like BZ. It will be you have a sharp increase inside BZ, you have sharp decrease of the density, such kind of criteria.
So it's just like checking thresholds, basically.
Yes, yes.
Yeah.
Also, people online, if you have any question, you can raise your hand. All right, if there are no other questions, thank you very much again, the speaker.
Thank you very much.